So once again, you'll draw a box like we did yesterday. And you need to interpret what this means by writing the particles in the box. I need at least one elemental gas in there, and then a molecular gas. Okay? And B, draw a gaseous mixture of two different elemental gases. Austin, you want to do that? How come? What's that? How come you didn't bring it back? Okay. Make sure you bring that next time.
Actually, no, it's because I did have kids.
Oh, you got one there. You got two.
I'm rich.
What you're going to read on page 211, once you get to some of you are going to get to that point, in it talks about what's called the collision theory. And the collision theory in physics or chemistry, depending upon what you're studying, is how chemical reactions happen. So we're going to look to see how a chemical reaction actually takes place at the micromolecule level. And then we have an excellent application of that I can show you. All right, where we have molecules actually collide and see what happens in different situations. That's okay.
So wait, does it just have to have a mixture of like 6 different molecules?
Just have 6 different ones in there. Yep. Yep, the six, I guess 6 different, I just say 6 total. So if you count how many would be in there, you count 6. They don't have to be different, as in each of those I just want 2 in that mixture. We know it's a mixture because you've got two or more different substances together, mixed together. Did I do that right? The second one, not so much. First one's close. I know. You're getting parts of it. Okay? And then turn to page 211, and you'll read 211 through 213. And then I'm going to ask questions about it, but it's pretty easy reading. Okay, just we'll go through it tomorrow. Just see what you got. Next one, we'll see what you figure out. So go ahead and copy this down. These are reactants. They're moving around. They might be hitting each other. Every time they hit, they'll get so much energy, potential energy. And they'll try to go up this hill. But this hydrogen peroxide, if I leave it sealed and not exposed to air and don't put anything in it, and guess what? Try to go up the hill. Can't go up. Can't go up. Alright? You ever have matchboxes you guys play with?
I play with fire all the time.
Match boxes?
Oh.
You know, like matchbox cars?
Oh, that.
Where you drop it and you have the ramps and you got the loop-de-loops and that. So, if you notice, you'd have to roll this fast enough so it get up, have enough energy, kinetic energy to get up to this point so it can go back down. And so this EA is called activation energy. Isn't there like a computer software games and that's an EA?
Yeah.
EA Sports. Okay.
It's in the game.
It's in the game. EA, it's in the activation energy. So, reactants now. If you notice, there's a little dotted line. Look what happens. Now this acts on a normal condition, like with this, under normal conditions, I put a catalyst with it, and boom, it goes right away. But if I don't put a catalyst with it, I'm going to do one for you tomorrow with this too, but in a different form. It's probably a little bit neater than this one. And if you put enough energy into it, it'll you won't have to go all the way to the top. It's kind of like digging a tunnel. Okay, make it easier to go through. You don't have to go over the mountain, we'll just build a tunnel. Less energy needed. So what it does is it lowers the activation energy, and that's called a catalyst. And then you form products. Right? So I'm going to give you some definitions in a little bit if we have time. Go ahead and keep your notes out. But I want to show you some of this taking place that help visualize it a little bit better. Okay. Here's our, I need to go back. Alright, here's our start. So these are under normal conditions. These molecules will be moving around. This is an elemental gas, and this is a diatomic gas. So this could be like argon and oxygen. But we know that they are not compounds. They will form a compound. Look, see, it'll form a compound. So it'll form two different products once it reacts. So we'll get it rolling. And this is exciting, let me tell you. Doesn't get much more exciting than this. That anticipation. When will they collide? And if they collide, will they collide with enough energy to get over that activation energy? Nope. That one didn't work. Come on. Nope. So they have to hit with enough energy that that bond breaks. If they don't have enough energy for that bond to break, if you notice that molecule's oscillating back and forth.
This is going to take forever.
You're probably right. It's kind of like taking that hydrogen peroxide and putting it in the genie bottle, not having a catalyst, and trying to get it to do what it did.
Let's do that again real quick.
Well, we'll do one tomorrow, similar to it.
We got to do something with it.
Oh, goodness, it just... Really?
And why does it hate us?
Maybe if we waited long enough, that it would do it. But you guys said we could heat it up, maybe. We could add a catalyst to it. We could make it a smaller volume so that when they do collide, they collide more often. And then maybe enough collisions, you'll get one of the collisions that will cause it to react. Let's go on. Let's not worry about this guy here a little bit. Right. Here's our potential energy diagram of reaction. And we've got a reactant, two reactants similar to what we had. If you notice, the activation energy is pretty high, but we need to get it up to that point so that we can get it taken care of. So this is kinetic energy, and this is potential energy. So this green one's potential energy, the red one's kinetic energy. Watch when they hit. So we're moving faster. That's good.
Break it.
Good. No.
Knock the snot out of it.
Come on, come on, come on, come on. Ooh.
Come on.
Kinetic energy, potential energy. The total of the two, this is potential energy of it.
Whack
This
that
is
sucker.
just, they just like,
Boom.
This has got me heated like an episode of Cops.
Here we go, here we go, here we go. Oh, we got it.
Bing.
We got it.
tap to
Oh.
the side. Oh, there's no.
Get him.
Another
Whack
cheese,
that
another-
sucker. It's like a game of Pac-Man.
Okay. So, we had enough energy for it to take place. And if you notice, the potential energy went down and the kinetic energy went up. So kinetic energy could be, it got hotter, it got warmer, created a situation like the genie in the bottle. When we handed it around, it got warmer. Okay, good. We'll go to this next one. You tell me the difference between this one and the next one, and what do you think about how long it will take to react? So this is the new one we want to do. Look at the activation energy diagram, and then look at this one. See the difference in the two diagrams. Okay. So we'll go to that next one.
It's going to take 10 years.
All right. So, how many think it's going to take longer? Raise your hand. Okay. How many think it's going to do it real quick? Raise your hand.
Oh, raise your hand, sure.
Okay, nobody raised their hand. And how many doesn't think it's not going to do anything? Huh? We're done.
I told you. I remember what I told you.
Activation energy is not very high, so the collision doesn't have to create a lot of force. So if it's high, then multiple times, and then eventually maybe there's enough energy where it can go. This one, it doesn't. Last one, got 4 minutes left.
Let's do like 13 more of those.
There's not 13.
12.
Okay, so this one, what we can do is we can add heat or cool it down. Yes.
Oh, yeah.
So let's cool it down. What do you what do you think's going to happen here if I have it too cold?
They're gonna like smooth extra slow. And of course,
Then we're not going to get enough energy.
we're just gonna sit there the whole time.
Slow motion.
Heat that sucker up.
Okay, so we heat it up. Get going faster. There we go. Come on, go, go, go.
Beat 'em up.
Heat up, heat up. Go faster.
Hit hard like mad.
What?
Oh, I've heated it up so hot that it came apart.
It wants to bond together. Do it good.
Actually put so much energy, oh, too hot. That's never happened before.
Oh, you broke her.
You
Go
broke
for it.
science. Nice job.
Man, it's just sitting there beating with
Why
that.
does science have to be so?
We'll get it. We'll get it right here. There we go.
Yeah, he done.
There we go. So, heat it up and maybe go faster, but then the bond might break a little bit too. Alright, tomorrow, Friday we're looking to do a lab. Tomorrow I will be here for the first part of the period. I'll get you going, and then I might have a video that you can watch. Okay? On what we're going to be doing in the other classes.